All right, line P1, learning task number 12, connect isolation transformers as autotransformers. We are on to 12D, where we're going to go through the 12th iteration of this autotransformer connection. Once again, this is an isolation transformer, 15 kVA isolation transformer, that we are going to go and reconnect so that it becomes a auto type of transformer. The last connection that we have over here, we see we're connecting a 1 to another 1 inside of here, or a same polarity to a same polarity. And they start by making a simplified autotransformer drawing of that application over here. Once again, it shows this drawing with a connection over here and this one pushing back down there. It is sometimes easier to visualize it if they would just draw, the other one kind of pushing back in like that, so that you then see sort of the, if I just put that onto there, the way that that second winding is kind of pushing away or cutting away from my primary winding. What we see over here is that instantaneously, whatever I have on X1 is going to be attached to my H1, right? Because this is going to have to go and follow whatever my polarity is on my source, meaning that this one is doing the same thing. If they're connected together, they would have to be into a series type of opposition. So let's start with that analysis over here. We see that we've got all of our polarities inside of here. This one's negative. This one would have to be negative as well. They're connected together. This one's positive 600. This one here is positive 120. And if I were to go and create the DC equivalent, it would be as if I have got a 120 volt cell in series with a 600 volt cell over here. What's going to win? Well, obviously, if I go and take a look at those vectors, draw out 120 and then draw out 600, the 600 is going to win. But the 600 is going to lose a little bit in the process, and it's really only going to be left with the net difference, which is going to be 480 volts that we'll have off of it. So our load is only going to go and see that 480 volts to it. Let's start putting some of those numbers back down over here. 480 volts. The other thing that I need to analyze is, where does all my load current pass through? Well, I see it passes through this winding over here. And if this winding over here is only good for 25 amps, which it is because it's that 15 kVA winding, that would mean that I could only ever get 25 amps out to this load over here. If I take that volts and that amps and I multiply it together, that would show me that the maximum kVA that I could possibly expect to get out of this transformer is going to be limited down to a value of 12 kVA. This is actually smaller than what the transformer's standalone rating was, right? It was a 15 kVA transformer. We are now knocking this thing down to a 12 kVA type of application that we are going to have off of it. All right, let's deal with this kVA thing as well. We also know that, once again, kVA in is going to be equal to my kVA out. If I have got 12 kVA out, I must have 12,000 kVA that would be heading in. And if I've got 12 kVA heading in, I could divide that out by the value of voltage, 120, to go and figure out my total amount of current that I'm going to have out of this thing. Total amount of current is going to be 100 amps that is going to be heading in, and 100 amps that would therefore have to be heading out, according to Kirchhoff's law of current. What else do I know about this circuit? A couple of things. I know that this is a positive over here instantaneously, which would have meant that this would have had to be the positive, and my current is going to be flowing through my load from negative to positive. So it's going to be heading towards this positive. That would mean this side's the negative, this side's the positive, and that my current itself would be heading in over here. It would also mean that if that current is heading in at a value of 25 amps over here, and if I'm getting 100 amps that is going to be flowing out of this one, that I would therefore need to go and have some other value of current inside of here. That would have to get placed through this. Now, there's a little bit of a disconnect inside of here in the way that this is drawn. Because what we started to do over here is we started to go and do this analysis based upon this polarity over here. The problem is this polarity is not the biggest voltage that we have inside of our circuit. And when I do it like this, what I would have ended up at would have been, 125 heading in, 25 heading in, and 100 heading out, and that would be a complete and total error. It just doesn't work. We don't satisfy Kirchhoff's law of current like that. Let's go and take a look at this thing one more time before we start drawing in these lines. First of all, we know that this is true, this value of kVA over here. We're good with the value of volts that we have. We're good with the current. With the maximum current we can pass through, there's 25 amps. It is going to be the 600 opposed to the 120 gets me the 480, and those two together give me this kVA. So I know that that's good. I also know that the 12 kVA that I would have to have over here is going to be good, as well as this 100 amp and this 100 amp that I'm going to have over here. But where everything else happens inside of here is all going to be dependent upon what this circuit on the inside sees as being my largest value of voltage. My largest value of voltage is going to be this over here, this 600 volts. Really, when I take a look at it, if I draw these vectors out again, 120 and then 600 in the opposite direction, I see that the 600 becomes the overpowering source inside of this circuit, which means that all of the polarities are not going to be fed in off of these lines over here, but inside of this circuit, all of the polarities are going to come out of here, which, if this is a source drives current from positive over to negative. Remember, this is the prevailing source inside of here. So if this is driving through from there to there, that would mean that that current would have had to enter in here, which would have meant that that current would have had to go through here, which would have meant that since this is a load, current flows from negative to positive through a load itself. This seems really counterintuitive. We'll get to this section up top over here in a minute. But what we have over here is we got this 25 amps that's going through there. That 25 amps is then heading into here. Once it heads in, that 25 amps is going to go and meet up with another 100 amps. This positive and this negative that we are seeing over here are not actually so much applied to this winding. We do see them on there, as we just need to look at them up top over here. This is, as a circuit as a whole, it is considered to be a load. Yes, it's made up of transformers, but the whole circuit, what this source out here sees, it just sees that it's got something that it has to deliver current to, so it will deliver that current in from the negative and take it back out on the positive over here. We've got this 25 amps that we have already done the analysis for, that it's going to have to go through like that. We've got this 100 amps entering in over here. 100 entering a node plus another 25 entering a node means that I must have 125 amps that is going to be heading through. That 125 enters into this node, where it splits off into the 25 as well as into the 100. We do satisfy Kirchhoff's law of current. Once again, look at these two sides that we have over here as well. This one is going to go and be a source. It has to be. Current flows through from positive to negative. It is the biggest source of voltage in there. Therefore, we need to go and follow the source rules for its values of current. This one up top has to be a load, right? We can never have two sources. We can never have two loads. We can only have one or the other when we're dealing with the transformer. So this one over here is going to have its current traveling through from negative over to positive. We are dumping some of those amps that we see inside of there in from this section over here. That's where we get to with all of these currents inside of here. Let's just go and put this one up onto our main one. Let's drop these values in that we have. 480 volts. 25 amps, 12 kVA that we have for this one. And then the last thing that we need to talk about is what is its setup. Well, we see that it's going from 120 to 480, so we would call this thing a step up type. We also see that these two are in opposition to each other, right? They're not helping each other out. I get 600 volts. It is not being helped by the 120, leaving it only at 480. So we would call this thing a bucking step up. I want to just highlight this one because very, very often I will hear apprentices and journey persons out in the trade that are just going to go and tell me that we need a boosting transformer. No, what you're looking for is a step-up transformer there. That's what you meant to go and tell me, but you just said boosting and bucking because you vaguely remember those, the terms from some time back in second year. This is the point where most of them pick up those terms and just misapply them. Bucking and boosting does not mean step up, nor does it mean step down. Over here, I see that I have got a bucking type of configuration, but it is still a step-up transformer that we have. Over here, I see that I've got a boosting, and it is a step up. Over here, I see I've got a boosting, and it is a step up. Over here, I see that I've got a bucking, and it is a step down. They are not tied together. That one can only ever be the other. So just, don't use those terms buck and boost unless you actually are comfortable in what those things mean. They just mean, are the windings opposing each other and screwing each other over, or are those windings helping each other out? All right, on the concept of buck and boost, let's just quickly talk about the last thing that we have inside of here, which is going to be our buck boost regulator. And the buck boost regulator is going to be used to go and maintain values of voltage that I'm going to go and have out. Now, if I take a look at my configuration that I have up top over here, I see that I've got primary lines heading into a high voltage winding, identified with H1 and H2, and then I have got secondary lines that are going to be heading out over here. Let's identify our current path. This is going to be a direct current path over to the secondary side. This is an autotransformer, so some of them are going to be passed all the way through. We also see that we are going to have this path over here for current. That is going to go and be my primary. And then when we get current through there, that is going to go and flux the core. And when it goes and fluxes the core, it is then going to generate values of voltage that we are going to have inside of here. Now, this switch over here for buck or for boost really just deals with which end of the transformer I'm going to switch to. If I want to boost the transformer, that would be an H1 to a X2 is the connection it's going to make, right? We see how that switch connects over to the X2 at that point. If I would go into a bucking configuration, it would connect my H1 down to my X1 at that point. So I would go and have this winding over here that would be subtracting out of the value of voltage that I would have from this winding over here. You use that switch to go and change that connection. Then the rest of these are just going to be tiny percentages. They're not huge that we're trying to go to. These are each going to be an additional 2.5% that we would be able to go and get out of these things. What we do is we then tap off from inside of here out to wherever we are. Let's examine the one that we have active at this point. If I take a look at the one that's active, I see that I'm in boosting mode and that I'm boosting in by, I'm just going to follow this one through till I get to the one that's connected there. 2.5% plus another 2.5% plus another 2.5% plus another 2.5%. And at that point, that's where I'm going to be taking my current back out to my load over here. So 2.5 plus 2.5 plus 2.5 plus 2.5 gets us to a grand total of 10% that we are going to be at. In position C, that corresponds. We are going to be at a secondary voltage that's going to be 110%. Where these are going to be utilized is usually by BC Hydro or, once again, large industries. They're going to have these things that are going to be constantly monitoring the lines, and then based upon what's happening out there, they're going to go and switch from component to component. You'll note that if I would rotate this thing in that direction, that for a split second, I would be bridging over top. Let's just see, maybe we can do this thing. Sometimes it doesn't allow me to draw over top, but we'll give it a shot. For that split second, I will have one here and one over there. And clearly it doesn't like that. That's one like that across there. These are going to go and be my reactors just for that split second as I'm in transition, as I'm moving from my position C to my position D. What these would allow me to do is divert my main current. So my main current would still be coming in on here and then going down and through that. And then I'm also going to go and have a smaller current. This winding here is still 2.5% of my primary lines. If my primary lines are, 25 kV, that's still a significant amount of voltage. And so what I have is I've got these two reactors over here that are going to go and form an opposition, a counter EMF, so that we don't directly short that out as we're transitioning from one to the other. They're pretty straightforward in their operation. They can be manual. They're more often than not going to be seen as being automatic. And they're going to be wicked fast. Everything inside of here is going to be a camming type of motion that's usually going to be done by spring wound, a spring that's going to be wound by a motor. You'll hear these things. If you've ever been around one, you kind of just hear that whole thing tensioning down. And then when they're ready to go and move from position to position, it sounds like a gunshot. It's just this big, loud, metallic bang as that thing fires over and kicks over. So we only have to go and do this little bit of snubbing for, just a couple of milliseconds at max. We can go and operate them under load. The only thing that we cannot operate under load is we cannot switch from boost to buck. If we do need to go and change, configuration in general from buck to boost, if for whatever reason, my primary lines were coming in way too high and we had to take off some voltage, then we are going to have just a brief shutdown so that they can go and reestablish this connection over here and then go all the way through. All right, that is it for learning task number 12.